In episode 40 of the SOC Level 2 training series, we're going to go through the Windows internals room, which is a part of the malware analysis module of the SOC Level 2 pathway of TryHackMe. And inside of the Windows internals room, we're basically going to understand the fundamentals of how Windows operates at its core, because most of the malware and most of the attacks that are done inside of the enterprise environment are done against Windows computers. And that's mainly because Windows computers are the easiest to manage when you have a large network of employees. So most enterprise environments, most companies basically use Microsoft Windows for their users because it's really easy to manage inside of Active Directory. And then they'll use Linux for the critical infrastructure, the systems, the infrastructure type systems too, because Linux is more lightweight and it doesn't really require a graphical user interface when you're dealing with some kind of a, let's say, a controller, you know what I mean, inside of a factory or something like that. So for end users, for individual employees, most likely it's Windows. Therefore, we're going to be talking about Windows. We're going to go through the introduction, the processes, threads, virtual memory, dynamic link libraries, portable executable format, interacting with the Windows internals, and of course, there's going to be a conclusion. We're going to do some final thoughts. We're going to do a review, and you will be dismissed for the day. That's pretty much it. And we do have a virtual machine that I've already launched, and it seems that the IP address has actually been assigned to us already, so we are ready to go. If you're serious about your CySec training and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the supporter, agent, guardian, and master. Each tier gets their own Discord server and early access to content. The agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us jump into Windows internals. For the average user of a computer, they have no idea what the hell is going on behind the scenes. So operating systems have a lot of stuff that's happening in the background that most people don't see, because they just see the graphical interface. They see their little mouse and then they click here and they click there. That's essentially what most people know of. Now, you obviously know that there's a lot more going on because you're literally studying cybersecurity. So you already know that there's more stuff happening behind the scenes. And this is what we're going to be talking about. This is the internal components of a Windows machine, specifically the Windows operating system, and the stuff that's actually happening behind the scenes that make the computer run and do what it is capable of doing. The objectives that we have are to understand and interact with Windows processes and their underlying technologies. We need to learn about core file formats and how they are used. And we're going to interact with Windows internals and understand how the Windows kernel operates. With Windows machines making up a majority of corporate infrastructure, because I already talked about that, red teams need to understand Windows internals and how they can be abused, right? So used, but abused. It's a very interesting way that they wrote this. I love that. The red team can abuse Windows to aid in evasion and exploitation when crafting offensive tools or exploits. So think about being on the red team, which means you are a pen tester, right? You're on the offensive security team, and you want to know how to use and, of course, abuse Windows to evade the stuff that Windows can do to detect you and ultimately exploit that Windows machine. Before beginning this, we want to make sure that we understand Windows usage basically, and the functionality. The basic programming knowledge that's inside of C++ and PowerShell is also recommended, but not necessarily required. I'm actually not that great at C++. I can kind of understand it. I can make sense of it. I am pretty good at understanding PowerShell because I've done a few videos on PowerShell already, and we use a lot when we do exploitation of Windows machines. But for your intensive purposes, there's a very powerful tool called an AI, and you can use AI tools like Gemini or Meta, whichever your favorite one is, and you can copy and paste the C++ code and be like, hey, can you just help me understand what this code is trying to do? And that way you can wrap your head around what's trying to happen. And then at the same time, you kind of learn how to read C++ code as well. So I'll probably end up doing that in these segments where I can't really fully understand what's happening. This is our virtual machine information. If you want to, if you're using TryHackMe yourself and you have access to OpenVPN, you can actually remote desktop into the Windows machine instead of starting it inside of the browser. I've started it inside of the browser just to make things a little bit simpler for myself. So I'm just going to be using the browser-based version of it. This is going to be the IP address for it, which is going to die at the end of the recording of this video. So this will no longer be available. And the username and password is right here. So, if you're trying to hack into this, I promise you're not going to be able to do it because it's not going to be available by the end of this recording. It's going to be tracked down. It's going to be pulled down. So that's pretty much it. There's some really, really good stuff that's ahead of us, and I'm excited to go through it. So we're going to click complete on the intro, and we're going to move into processes. You can think about a process as the entity, right, that maintains and runs the program. Or when a program is running, you'll see in the list of processes a process name that is associated with that program. A lot of times applications actually use one or more processes, and it has a lot of different components, and it gets broken down into the storage, or it can be broken down to be stored, and you can interact with the various elements of that application or those various processes. Inside of Microsoft Docs, they break it down as this. So each process provides the resources needed to execute a program. A process has virtual address space, executable code, open handles to system objects, a security context, a unique process identifier, also known as a PID, environmental variables or environment variables, a priority class, minimum and maximum working set sizes, and at least one thread of execution. That's a lot of data to wrap your head around. Don't worry about it if you didn't understand that. I mean, hopefully, I think by now you should know what a process is. But in case you didn't know what all that means, not that big of a deal. We're going to go into it. This information might seem intimidating, but this room aims to make everything a little bit less complex. As previously mentioned, processes are created from the execution of an application. So just keep that in mind. They are core to how Windows functions, and most functionality of Windows can be encompassed as an application and has a corresponding process. These are some examples. MSMPENG is Microsoft Defender. WinInit is keyboard and mouse. And LSAS is credential storage. LSAS is a very common one. We do LSAS dumps using something like Mimikatz or something like that. So we've used this a lot in exploitation exercises. But MSMPENG, Microsoft Defender, WinInit to initialize the keyboard and the mouse and to use the keyboard and the mouse. So attackers can target processes to evade detections and hide malware as legitimate processes. This is the smallest of potential attack vectors. So process injection, this is the ID inside of the MITRE attack framework, the attack matrix. Process hollowing, this is the ID. Process masquerading, this is the ID. So if we open this, it will most likely open up, MITRE attack for us. So process injection, right? And then you can go through the description, you can see the various examples and the IDs and the names of the organizations that actually used them, and there are going to be reference sources at the bottom, as well as mitigation and detection techniques that you can use. And then, of course, these are all the references for this specific thing. So all of these have a MITRE attack page that you can go and read a bunch of data for it. And MITRE attack is one of the most powerful things that we've used thus far inside of our SOC level 2 and even SOC level 1 activities, because it's just a massive data of actual attacks that have taken place inside of the real world and the data that was pulled from it, the lessons that were learned from them. Processes have many components that can be split into key characteristics that we can use to describe processes at a high level, and the table below describes each critical component of processes and their purpose. Private virtual address space is virtual memory addresses that the process is allocated. Executable program defines the code and data stored inside of the virtual address space. Open handles defines the handles to system resources accessible to the process. Security context is the access token defining the user, the security group, the privileges, and other security information. The process ID is the unique numerical identifier, and the threads are the sections of a process scheduled for execution. So these things are actually all feed into each other, right? So starts up here and it just works its way downwards. We can also explain the process at a lower level as it resides in the virtual address space And this is what that breaks down to. So the code is the code to be executed. The global variables are stored variables globally, meaning across the entire system. Process heap defines the heap where the data is stored. Process resources defines further resources of the process. And environmental block, data structure to define process information. Process resources can also be considered the dependencies or requirements. These are the further resources of the process that it's using or it provides for use for other things, and the data structure to define the process information. So we have an image right here. You have the full job, right? And then within the job, there's all these individual processes, or the elements of the process, I should say. So code, global variables, process heap, process resources, open files and heaps, environmental block, and then thread 1 through thread however many. This information is excellent to have when we get deeper into exploiting and abusing the underlying technologies, but they are still very abstract. We can make the process tangible by observing them in the Windows Task Manager. And a task manager can report on many components and information about a process. Below is a table. So it'll give you the name, it'll give you the PID, the status of it, and the username that's actually running it. So for example, conhost would be the name of the executable that's running. 7408 would be its process ID. It is currently running, and the owner is the system. The username that's actually running it is the system. And if it's running on a system level, that means it has system permissions. So keep that in mind, right? So if you can actually manipulate this specific executable, that means it's going to continue to run with system permissions. Keep that in mind. They're what you would interact with the most as an end user or manipulate as an attacker. There are multiple utilities available that make observing processes easier, including the Process Hacker 2, Process Explorer, and ProcMon, Process Monitor. These are all things that are available. I think these are the connections to the rooms. Oh no, these are the GitHub repositories for these things. So System Informer under Winsiders, I think that's how you pronounce that. So we have System Informer, Process Explorer. And this is on Microsoft's official website, because this is a Microsoft official software application that's available. And ProcMon should also go to Microsoft, because this is also a Microsoft unique application that's available for us. The process at the core of Windows internal components and Windows tasks will extend the information about processes, and we will go through them. The following tasks, we will go through them. Open the provided file, log file PML in ProcMon, and answer the questions below. So let's go ahead and do that. So what I'm going to do to make our life a little bit easier, I'm just going to keep this portion of the page zoomed in, and I will go ahead and this is going to look really weird right now, but once I go into full screen, we'll be able to access it a little bit easier, and I'll just shrink that back down. And once it's in full screen, we'll be able to actually go back and forth between the device and be able to do a bunch of cool things, answer these questions. So we're looking for logfile.pml, and we're going to open it in ProcMon. So let's see if we can do this here. All right, so on the Windows machine, there's a little folder called Process Monitor. So if I open this thing, it will bring these things up for me. I'm just going to open up the basic version right here, the application itself. It says, do you agree? I agree. Open the application for me so I can open up the log file. And it's actually inside of that same location. As you can see, inside of this, we actually have the log file, the ProcMon log file, etc. I believe that's the one that I'm supposed to be opening. So we will go to Process Monitor, we'll click File, we'll click Open, and then we're going to navigate to that file. It's already here, so there you go, log file, and we're just going to open that. It's a .pml file, and we're going to give it a second, and it will open, and we'll be able to access the data. So there we go, it's loading. All right, cool. So here we go. This is it. So I'm just going to expand some of these things a little bit to make it a little bit easier for us to read through them. The paths are going to be fun. We need to get that information, and the details are most likely very important as well. All right, so what's the first question? It says, what's the process ID of Notepad exe? So you have the process name, right? And then you have the PIDs. So if we click on process name at the top right here, it should technically just organize it for us by name. So let me see if it's actually going to do this. Okay, so we can't click on this thing, but there's a filter option. So let's see if I can filter by something. So architecture is, let me see if I can do name maybe. So if we do process name, boom, there we go. Process name is, and then we will do notepad.exe, And then let's do that and see what we can find. You did not add the item that you were editing. Added now. Okay, we'll do that. And there you go. Notepad.exe is 5984 is the process ID. So let's see if that's actually the answer. It is. Excellent. What is the parent process ID of the previous process? So we're looking at this, right? So process name is Notepad.exe, and we're looking for the parent process ID. So parent process ID, it actually says it right here. Parent, okay, bro. Parent PID is right there. If I hover over it, I'm sure it's going to do that same thing again. Yeah, there you go. That's annoying. So parent PID is 3412, as we can kind of see right here to make it a little bit easier. So it was, what was it? 3412. So let's try that. And that is true as well. What is the integrity level of the process? That's interesting. So let's see if we can find an integrity level here. All right, so here's how I found this one. I just double clicked it. I went to process, and then right here, there's a level called integrity, or a field called integrity, and the value is high. So integrity level of this is high. And that's it. All right, cool. Let's move on to threads. So a thread, as we saw earlier, is inside of the process, right? So it's an executable unit that's inside of the process or employed by the process. And it's scheduled based on the factors of the device. So the factors of the device could be, the CPU and memory specifications, priority and logical factors, and other things. So it's basically an executable inside of the process itself. And we can simplify the definition by saying controlling the execution of a process. That's what it does. So since threads control execution, this is a commonly targeted component, and thread abuse can be used on its own to aid in code execution, or it's most widely used to chain with other API calls as a part of other techniques. Threads share the same details and resources as their parent process, like the code, the global variables, and they also have unique values and data outlined in this table. So you have the stack, which all the data relevant and specific to the thread. So for example, exceptions, procedure calls, etc. I need to slow down a little bit. I'm kind of like overly caffeinated. Thread local storage, pointers for allocating storage to a unique data environment. Stack argument, unique value assigned to each thread, and the context structure holds machine register values maintained by the kernel. They may seem like bare bones and simple components, but their function is critical to processes. So we're going to open the file log file PML in procmon and answer the following questions. So it's already open, so we're good. What is the thread ID of the first thread created by Notepad.exe? So I think we're looking for chronological, right? Operation thread is, okay, so it's listed as the operation thread create. So we're looking for an operation called thread create, and we're looking for the first thread, which I'm going to guess that based on just the timestamps here, 721.3, and they're increasing. So this is the very first one. So operation is process start or thread create. There you go. So the first one that has operation thread create. And the question says, what's the thread ID of it? The thread ID is right here, 5908. So we're going to go over there and do that. Very good. What is the stack argument of the previous thread? And this is listed as thread in the event properties. So if we go to this and just open this up, and we're looking for event properties under the stack right here. Whoa, there's a lot of information. And event is available over here as well. And so date thread 6544, let me see, stack argument of the previous thread. So the stack argument, let me see if I can find that. So the only thing that's listed here under thread is 6584. So I wonder if that's what it is. So let's see if we can do 6584. Oh, that is it. So the stack argument is just this number that's listed under thread under 6584. So great, we were able to find that. And now we can move on to virtual memory. Virtual memory is how internals work and interact with each other, and it allows internal components to interact with the memory as if it was actually physical memory without the concept of collision. So without collisions between applications, and we'll be talking about what that is in a little bit. Virtual memory provides each process with a private virtual address space. A memory manager is used to translate virtual addresses to physical addresses. By having a private virtual address space and not directly writing to physical memory, processes have less risk of causing damage. And it probably also will end up getting wiped because it sounds like it's a part of the RAM, the random access memory, which is volatile memory. So if it's not being written directly to physical memory, most likely this is going to be wiped. But let's see if that's actually the case. The memory manager will also use pages or transfers to handle memory. Pages are essentially just chunks of data, so you can think about it that way. Applications may use more virtual memory than physical memory allocated. The memory manager will transfer or page virtual memory to the disk to solve this problem. And we can visualize it like this. So you have virtual memory. So there's virtual memory, we have physical memory, and then we have virtual memory. So, this block is being sent to this chunk of physical memory. This block is being sent to this one. This block is also being sent to this one. This block is being sent to this one, so on and so forth. And then from here, this one is going to go to the disk, and this one is going to go to the disk. And then you have the individual processes that are running inside of these things. So it seems that not everything is going to actually be written to the disk, and not everything is going to be written to the physical memory. So it's kind of selective, right? So the memory manager will transfer or page virtual memory to the disk to solve the problem. The theoretical maximum virtual address space is 4 gigabytes on a 32-bit x86 system. We talked about the x86 architecture in the last 2 videos. The address space is split in half. The lower half, which is these chunks right here, is allocated to processes as mentioned above. The upper half, these chunks right here, is allocated to OS memory utilization. Administrators can alter the allocation layout for applications that require a larger address space through settings, increase user virtual access, or the address window extensions. So what they're talking about right here in the 32-bit system, this is the example that we're talking about. Assuming that it has 4 gigabytes of virtual address space, the top 2 gigabytes are going to be addressed right here. You can to processes as mentioned above, and then the upper half is for OS memory utilization, So my bad. So the bottom half will be to the processes that were listed above. The upper half would be the processes for the OS. And then in this particular case, you have a 64-bit system over here that has 128 terabytes, which is insane. I don't even know what system. That's like a massive system. How is that even possible? I know how it's possible, but it's like that's a really big freaking system. 128 terabytes, dude. That's insane. And that's just one chunk of it. So technically it's 256 terabytes. That's insane. That's a lot of space. Whew, that's massive. It's like probably like a giant data server or something. Administrators can alter this allocation. Okay, we talked about that. The theoretical maximum virtual address space is 256 terabytes on a 64-bit modern system. So theoretically, it's 256 terabytes. The exact address layout ratio from the 32-bit system is allocated to the 64-bit system. Most issues that require settings or the are resolved with increased theoretical maximum. You can visualize both of the address space allocation layouts to the right. Although this concept does not directly translate to Windows internals or concepts, it's crucial to understand. If understood correctly, it can be leveraged to aid in abusing Windows internals. So yes, I understand that. What is the total theoretical maximum virtual address space of a 32-bit system? That would be 8 gigabytes. And what is the default setting flag? What default setting flag can be used to reallocate user process address space? And it was the thing that was inside of this right here. Increase user VA. That would be the answer, I believe. And open the provided log file in Procmon and answer these questions. All right, so what is the base address of Notepad.exe? And it's going to be listed as the operation load image, the base address of Notepad.exe. So let's go here. And the operation address image, right? The operation load image, my bad. So the operation load image of Notepad.exe. So let's zoom in a little bit. And we'll just open the first one here. And we want the load image. So let's see what we can find here. Oh, I see. So this is what it's asking. So this is what it means when they say the operation load image. So inside of the operation load image, the image base is right here. This is what they're saying. Okay, that makes sense. I should have looked at other things. So, okay, this is the location. Now I need to be able to pull that information. So let's see how we can copy that to use for our answer here. Oh, there we go. Image base. Boom. Take that, copy that, and that should be the answer that we're looking for. Excellent. Cool. Let's talk about dynamic link libraries. Per Microsoft Docs, a library that contains code and data that can be used by more than one program at the same time is the dynamic link library. So since it can be used by more than one program at the same time, it feeds into the concept of it being dynamic. They're used as one of the core functionalities beyond application execution in Windows. From Windows documentation, the use of DLLs helps promote the modularization of code reuse, efficient memory usage, and reduced disk space, so the operating system and the programs load faster, run faster, and take less disk space on the computer. I will let you know right now, though, like most of the freaking computers that I've ever used at my jobs in the past that have been Windows were slow as hell. So it's like, yeah, I guess it's supposed to make things load faster, but like, really though, bro? It does not. It doesn't, though. I'm just saying. When a DLL is loaded as a function in a program, the DLL is assigned as a dependency. Since a program is dependent on a DLL, attackers can target the DLL rather than the application to control some aspect of execution or functionality. And these are some techniques: DLL hijacking, side loading, and injection. And if you want to read more about them, you can go to these individual IDs inside of the MITRE attack matrix. DLLs are created no different than any other project application. They only require slight syntax modification to work. Below is an example from Visual C++ Win32. So include this, define this, include this, and bool, I'm guessing is boolean, excuse me. And then we have this, return to. So let's see what it says. It will define the functions as imported as exported. We will discuss the header file's importance or lack of in the next section. These are the header for the DLL file. So is this the actual DLL file? This is the DLL file itself. So this is the DLL file, and then we have the header for the DLL file that we saw, the defined portion of it, etc. So these are the DLL has been created, but that still leaves the question of how are they used in an application, and they can be loaded in a program using load time dynamic linking or runtime dynamic linking. When loaded using load time dynamic linking, explicit calls to the DLL functions are made from the application. You can only achieve this type of linking by providing a header, which is .h, which is what we saw actually right here. So this is what that is. This is the .h for the header. And then what else we got? And the import library, which is the lib. Below is an example of calling an exported DLL function from an application. So it's been exported from an application. We are now including it or importing it. So that's the header, and this is the DLL, the library. And then we are now going to, I guess, call on it. And I don't know C++, and I don't want to take too much time to try to break this down, but you can definitely take this into something like Gemini AI or GPT or whatever your favorite AI is, and it'll explain it to you like it's nobody's business. So when loaded using runtime dynamic linking, a separate function, the load library or the load library EX, is used to load the DLL at that time. So if we go over here, do we actually see that? We don't see that. So I guess it would be at the bottom right here. And this is essentially what the function is going to do. I think it's just going to call on the hello world function. Once loaded, you need to use the get process address to identify the exported DLL function to call. Below is an example of loading and importing a DLL function into an application. And so this is an example. It's not necessarily necessary to understand what this is. But you have the hello world variable that equals this, and then if hello world is null, meaning it's nothing, then you call it, I guess, or you will call on that as the else portion. So in malicious code, threat actors will often use runtime dynamic linking more than load time dynamic linking. This is because a malicious program may need to transfer files between memory regions, and transferring a single DLL is more manageable than importing using other file requirements. So we're going to look at this in Progmon again and answer the following questions. So what is the base address of ntdll.dll loaded from Notepad, and it says listed in the operation load image of ntdl.dll. So we're going to look at the operation load image that says nt, so load image right here, and we want this one right here, so ntdll. And what is it looking for? They're looking for the base address that would be available here. So the base address is this piece right here. So let's copy that and go over here and paste that. What is the size of the ntdll that's loaded from Notepad and found in the process tab of the event properties? So process tab of the event properties. So this is where we are, process tab, and we're looking for the size of this thing. See if we can find it. It is right here, but I wonder, so can I copy this? How can I copy this? Oh, there you go. That opened up. Do I have the size? I don't have the size. That's unfortunate. So do I have to manually type this? That would suck if I had to manually type that. Okay, fine. It's what is it? 0x1ec000. So let's see if we can do this. 0x1ec000. There you go. How many DLLs were loaded by the Notepad? Filter the operation by load image in Procmon, and we're going to look for DLLs. So we're going to now go here. We're going to filter the operation, and we're going to filter it by load image in the Procmon. So let me see if I can even find that. And if possible, then we will go ahead and see what we can do. So we'll do process name in this case, and we will do notepad.exe and include, okay, so there we go. We filtered the operation. So when you go under filter and you want to list it under this list right here, you want to click on operation and then right here type load image, and then you'll get this right here. And so what is it asking us? It says how many DLLs were loaded by Notepad. And so now we're looking for all of the DLLs that were loaded, and it seems to be a lot of freaking things right here. So if I go from here, and I guess I can just highlight all of them, it seems to be pretty much all of them are DLLs with the exception of just a few. Let's see. So if I highlight all of them, so let's see if we go all over here, does it tell us how many yeah, so 53. So I would say it's either 53 or 52. I just don't know if this one right here is, oh, that is also a DLL. So it's 53 in total. So let's see, 53. The answer is incorrect. What's the hint? It just says load image in Procmon. So it seems like it's 53 though. I mean, the one at the very, very top right here is the Notepad executable itself. So all of these things, it's just asking for DLL, right? So am I missing something? Let's see. Okay, so there are two things that, so when you highlight all of the DLLs, there's 53 of them. There's one that is like a where was it? You kind of analyze through them and it'll show you, it's a DRV right here. So there's that, we subtract that. And then this one right here, or one of the other ones is a capital, there we go, this capital DLL. I don't think that counts either. I don't know why it wouldn't count, but I believe that's the only other one. So I basically subtracted 2 from 53 and it gave me 51, and that was the right answer. So that is that, and now we can move on to portable executable format. All right, so executables and applications are how Windows internals operate at the higher level. The PE, also known as the portable executable, this is a formatting that defines the information about the executable and its stored data. So the PE format also defines the structure of how the data components are actually stored. Its overarching structure for the executable and object files and portable executable and COF, so common object file format, make up the actual PE format. So if we look at this right here, the header is the PE format, and this would be the definitions of the things and the file structures, right? And then you have the contents, the actual sections right here, which is the code and the imports and the data itself. And this is what makes up the file executable. So inside of the PE, inside of the header is where the information about the executable and its stored data is defined, and it also defines the structure of the data components and how they are stored. The PE is most commonly seen in the hex dump of an executable file, and we will break down what that is for calc. So in the inside of the PE, inside of the portable executable, we're going to look at the calculator executable to see what that looks like. So the structure of PE data is broken up into 7 components. The DOS header defines the type of the file. The MZ DOS header defines the file format as .exe. So let's see right here in hexadecimal, that MZ right there defines it as executable, and the DOS header can be seen in the hex dump section below, so we can see it right there. The DOS stub is a program run by default at the beginning of a file that prints a compatibility message. This doesn't affect any functionality. The DOS stub prints the message. This program cannot run in DOS mode. The DOS stub can be seen in the hex dump section below. So you see it right here. This program cannot be run in that mode. You can see it. The PE file header provides PE header information of the binary, defines the format of the file, contains the signature and the image file header and other information headers, and it's the section with the least human readable output. You can identify the start of it in the section right here. So you can see that right here, and as you can see the rest of it. So this is the header, the PE, and the rest of it on the right hand column right here. You can't make sense of it. It's literally mostly dots, like the majority of it are dots. The image optional header has a deceiving name and is an important part of the PE file header. The data dictionaries are part of the image optional header. They point to the image data directory structure. The section table will define the available sections and information in the image. As previously discussed, sections store the contents of the file, such as the code, imports, etc. And you can identify each section right here. So you have text right here. And I think it's actually cut off because I'm a little bit zoomed in too much. So let's see if I zoom out a little bit, if we can see that easier. So there you go. You could see text, you could see R data, data again, P data, etc. So it's the codes, imports, and other data that we can see inside of the hex portion. Now that we've defined a format, these sections can actually be seen like this. So .text would be executable code and entry point. .data is containing initialized data, so strings and variables. R data or I data contains imports, which is the Windows API or DLL. So you can actually see it, right? .data, or excuse me, .text. You have .r data right here. Again, more .data. And let's see, .p data is available over here. So we can see all of those things. We have .text, .data, R data or I data. .reloc is the relocation information. .rc or rsrc is the application resources, and then debug is the debug information. So we can actually see most of those here. We have the text, R data, .data, P data, rsrc, and relocation as well. So all of that stuff was there. So what PE component prints the message this program cannot run in DOS mode? And we have that up here. So this is the DOS stub that is available for us. So let's go look at that right there. And we're going to look at the Open Notepad .exe in Detected Easy and answer these questions. So let's go here and let's see if we can actually find Detected Easy. I think it's a new, or it's a different software that we're supposed to be using. Okay, so there's die right here is Detected Easy. Goodness, bro. The stuff that these guys do to us. Okay, so all right, so open this in Detected Easy, and what is the entry point? Reported by die. There you go. I should have probably just looked at that first. What's the value of number of sections? What is the virtual address of .data, and what string is located in those sections? So let's see, what's the entry point reported by it? Let's see how long this takes. Okay, cool. Here we go. We have it here. We want to open notepad.exe. So I need to go ahead and find Notepad specifically. I wonder if I can just browse to it, or if it's something that I need to actually find inside of the PC's programs, etc. So let's go and try to just kind of find the program itself. Okay, so I searched for Notepad inside of the search box, and then I right-clicked it and I said open the location of this file. And so we can see the location is this full path that I did right here. So let me click back one more time and there you go. That gives you the full path. So see users, THM attacker, app data, roaming, etc., etc. So I'm going to just kind of keep this right here, and then we're going to find it using that location. So we're going to go to local disk, we're going to go to users, and then we're going to go to THM attacker, and then we're going to go to, oh, I can't find app data. Brilliant. So maybe I can just do it like this. So I will do app data like that, press enter like that. So we can do it like that. So we'll actually type the whole thing over here. There you go. And we can now click on Notepad and then open Notepad. Okay, so here's some interesting data for this thing. So we're going to expand this and see what we can find. This is a lot of tiny data. Oh my gosh. All right, what's the entry point reported by DIE? So I'm looking for the entry point. And it's right here towards the top right there. So that's the entry point. Let me see if I can right click and copy that. So hopefully that actually copied. Okay, great. What is the value of number of sections? So let's try to find that. It's right here. So it's actually called sections, and the value is 0006. So that would be it. And what is the virtual address of .data? So let's see where that would be. Okay, so this was this was difficult to find. So the hint tells us to look in the PE window, and I was looking for an entirely different application, but there's actually a button right here, the PE button, and it'll open this up right here. So now we can actually look at the section they're talking about, which is the section tab of the PE window that's asking for the virtual address. So section tab of the PE window, which I think I might be here. So let me see if I can find the section tab for sure, and then get the virtual address. All right, so sections is right here on the left menu right here, and a virtual address is right there. And they want it for .data. So we're going to look right here, and that's the virtual address. So let me see if I can edit this, and whoops, there it is. And so there is that. If I can copy that, that would be great. And then paste that and submit it. There we go. And what string is located at the offset of, we'll say 99C, and that's in the strings tab. So let's go to the strings tab, and then we're going to look for 99C. So let's find 99C, and there we go. So if you organize it from smallest to largest, it's line 170. And the string itself here is Microsoft Notepad. All right, here we go. Interacting with Windows internals. To be able to interact with Windows internals, you can do it relatively simply or easily through the Windows API calls, and they provide a network native functionality to interact with the Windows OS, and the API contains the Windows 32 API and Windows 64. We'll only provide a brief view of a specific few API calls relevant to Windows internals, and there is the Windows API room. That's exciting. I'm very, very excited to actually learn about that. That's something I know for a fact. Yeah, I have not done this. I would love to learn how to interact with Windows through APIs. Most Windows internal components require interacting with physical hardware and memory. The Windows kernel will control all programs and processes and bridge all software and hardware interactions. This is especially important since many Windows internals require interaction with memory in some form. An application by default normally cannot interact with the kernel or modify physical hardware and requires some kind of an interface. And this is solved through the use of the process modes and access levels. Windows processor has a user and kernel mode. The processor will switch between these modes depending on access and requested mode. The switch between the user and kernel is often facilitated by system and API calls and documentation. This is sometimes referred to as switching point. So the user mode, no direct hardware access. Kernel mode, direct hardware access. Creates a process in a private virtual address space in user mode. Ran in a single shared virtual address space in kernel mode. Access to owned memory locations in user mode. Access to entire physical memory in kernel mode. So obviously kernel mode has a lot more power than user mode does. So we can see it right here. The switching point is basically the point between the user mode or also known as user land, and kernel mode, which is pretty much the system and the nitty gritty. So you have the user application. I think I should stay out of that. So user application right here, the API, the Windows 32 API that actually interacts with the system calls, or the portion where you can actually start interacting with the kernel, and through the API and the calls of the system, you'll be able to interact with the kernel, which is controlling the physical memory and the hardware. So applications started in user mode or user land will stay in that mode until a system call is made or interfaced through an API. When a system call is made, the application will switch modes. Picture right is the flowchart. When looking at how languages interact with the API, this process can become further warped. The application will go through the language runtime before going through the API. The most common example is C executing through the CLR before interacting with the Windows or Win32 API and making system calls. We're going to inject a message box into the local process and demonstrate proof of concept to interact with it. The steps are as follows. Allocate local process memory for the message box. Write, copy the message box to allocated memory. Execute the message box from local process memory. At step 1, we can use open process to obtain the specified process. So we will use, this is C language, this is not C++. So we're going to handle the process, open the process, right? And then at step 2, we can use virtual allocation executable to allocate a region of memory with the payload buffer. So this is where we see right here, this function right here, and the size of the payload right here. At step 3, we can write the process memory to write to the payload allocated region of the memory, and this is the function, and we can see the details right here. So open target process, allocated memory region, data to write, byte size of the data. At step 4, we will use the create remote thread to execute the payload from memory. So this is a variable, and then we're now creating the remote thread function. So open the target process, default size of the stack, pointer to the starting address, and immediately after creation is the value of 0. So we're going to open the command prompt and actually execute the provided file that's inside of our injection folder and answer these questions. So let's go ahead, and I can now close this so I no longer need this. It was an interesting tool though. So we're going to go right here. We will open up a command prompt by going to cmd.exe. I'm already inside of the user's attacker. So what I need to do is I need to go inside of my desktop to be able to get access to the injection. There we go. That's where we need to go to, process injection. So let's do that. I don't know why they spaced it out. Process injection. There we go. And now in here, we can see that we have the executable. So we could basically just do this, I think. So inject-poc.exe. And there you go. It just popped up. There's a little message that popped up. I don't know if I could copy this. Can I copy this? Oh my God. Why are they making it so difficult right here? So enter the flag obtained from the executable window. They want me to manually type this. These guys are kidding, dude. I don't want to manually type this. What if I clicked OK? Will it be inside of this? No, it's not. So I have to actually run it and try to capture this somehow. Godly. Okay, manual typing it is. Let's drag this off and we will type it manually. Okay, so the key point here is that this is actually case sensitive and all of these things need to be done correctly. This is a lowercase l, this is an uppercase L. I thought this was an I, like a capital I, but it's not. It's a lowercase l, this is an uppercase L, and the rest of it is exactly as you see right here. It is case sensitive, so keep that part in mind. And yeah, that's it for that last one. So let's go into the conclusion here. So the key point that we take away from this is that Windows internals are the core of how the operating system actually works, and they cannot change without compromising the operating system. And that's why they're so attractive for attackers. So literally they are the building blocks of how the operating system inside of network or inside of a Windows computer works. And so if you can modify them somehow, then you can modify the way that the system works. And if you can actually modify them without stopping the functions of the system, so it appears as if the system is just running normally, but in the background it's actually doing something that you want it to do as the attacker, then you have accomplished, your job, your task. The attacker can easily abuse the functionality of Windows internal components for nefarious reasons. For more information, there's the Abusing Networks Internals room. And many of the concepts covered in this room can even translate to Unix counterparts. While specific of the attacks and how they're executed may change, many of the core concepts stay the same. Overall, Windows internals are here to stay. Both red and blue teams need to be aware of their capabilities, including how and why they are used. So this video and the last two videos were very, very detail oriented for me. I followed instructions essentially to be able to get the answers that we needed for them. And this was a learning curve. I went through a learning curve with these videos. So I did my very best to try to kind of like break things down as I understood them. But for the most part, as you saw, I was kind of just reading through everything. So hopefully it made sense to you. Hopefully you were able to get the information and get the answers that we needed and all of that good stuff. But for the most part, this was definitely a learning experience for me. It was a learning curve. And I think that's basically what it's going to be like for the rest of the malware analysis module, because it requires very detail-oriented review of very detail-oriented stuff inside of these computers. So we're really looking at the core functions, the building blocks of a computer, not so much the application level stuff. And I mean, I'm enjoying it because I'm learning, but this is stuff that I have to review and re-review to make sure that it actually clicks for me. So if you're having a hard time grasping it, don't worry, we're both in the same boat, basically. That's basically what I'm trying to say. So we're going to click complete and we'll be done. All right, so congratulations. I hope you got to the same end result that I just got to, and you were able to get all of those answers. And if you want to find more videos like this one, especially as we wrap up the SOC Level 2 pathway of TryHackMe and our just general SOC Level 2 playlist that we have, and as we graduate to PenTest Plus, we have more videos that drop every single week on Fridays for PenTest Plus. And then, of course, there's going to be, right after SOC Level 2 is done, I can now move into the AI for cybersecurity, which is a really, really big piece. So all of those things, to be able to get access to all those things, make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out. And you will be able to get, obviously, access to all those things. And you can drop a comment in the comment section below if you have any questions for me, or if you want to just say that you also had a learning curve as you went through it, just so we can kind of be in the same boat. But that's pretty much it for the video today. So just make sure again that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out in SOC Level 2, in PenTest Plus, as well as AI for cybersecurity, and of course everything else that we're going to end up doing for TryHackMe as well. If you're serious about your CySec training and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there. Or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comments section. And that is it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease, and I'll see you in the next video later.